All right, so I'm going to go over the solution to the pair competition problem that we all did in class. So we're looking at this water bath with a wall on the east side, and we're asked to find the total force or the net force exerted on the wall by the fluids. Of course, the wall has fluids on both sides of the wall. It's got atmospheric air. It's got air on the right side. It's got water and air on the left. And so we're going to try to calculate the net force. The top of the wall, the top meter of the wall, has atmospheric air on the right and atmospheric air on the left. So the net force contribution from that part of the wall, the top 1 meter of this 6-meter wall, is going to be 0. So we're going to ignore that top meter because it's got pressure on both sides that are balancing each other. The atmosphere is pushing it, from the right and from the left equally, just as you are balanced with that. There's atmospheric pressure on the front of you. There's atmospheric pressure on the back of you. They're both pushing very hard, but you don't even notice because they're balanced. So we're not going to worry about that. We are going to worry about the bottom, 5 meters of this, where there's water on one side and air on the other. So those pressures are going to be quite different, and that's going to lead to a net pressure. So the P on the right-hand side, it's just atmospheric pressure. Plus, as we get deeper, the pressure of the air goes up a little bit. So it's rho air times G times that minus Z. I've set my coordinate to be here at Z equals 0 at the top of the water. You don't have to do that. We could put it at the bottom of the pool. Doesn't matter. Just make sure you know what you did and integrate appropriately to the right limits. I've chosen to have Z equals 0 be at the top of the water. So I'm going to have minus Z here because as Z goes negative, this is going to go up in pressure. And same thing on the left. It's going to go, up in pressure as Z goes down because negative Z goes down. So there's going to water side on the left. We're going to have more pressure on the water side. It's going to be P naught plus rho water times G times Z. So got that. Now, if P were constant, the calculation to calculate force is very simple. You just take force equals pressure times area. But you can't do that if P is not constant. P is variable. So I have two integrals I have to do. So instead of just P times A, I have to integrate over that whole surface A. So that integral is going to be in two directions. It's going to be in Y and Z because the wall is, normal to the X direction. So the surface is a YZ plane surface. So I'm going to integrate in Y from 0 to W. That is the width of the wall. And I'm going to integrate from Z to minus 5 to 0, which is from the bottom of the tank to the top of the water. And so normally I wouldn't include this integral from 0 to W because I already know it's just going to come out to be W, but I'm just showing it to you this time so you see why that is. So the issue is that when I'm integrating from 0 to W in Y, there is no Y dependence of pressure here. The pressure only depends on Z. So there's no Y in this equation, no Y in this equation. So they're just constant in the Y direction. So you don't need to do any fancy integral. That integral is just the integral of from 0 to W of dy. And the integral from 0 to W of dy is just W. So I would expect in future you not to have to do this integral. You would just recognize right away that if the pressure is constant in this direction, you can just take W and just put it in there. So we're going to go ahead and do that now. We'll go ahead and say that this integral on the right-hand side, the force on the right-hand side of the wall is equal to negative 5 to 0, times W times P naught minus rho air GZ dz. So I have that W there, and that's a constant, so I can actually pull it out of the integral entirely. I'll do that in the next line. And on the left-hand side force, it's the same thing, right? It's still going to be W, and it's going to be minus 5 to 0 times P naught minus rho water, now G and Z and dz. Notice that I have a negative sign here on the right-hand side because that force is pushing back in the negative X direction. So this is going to be a negative force if there's pressure on this side of the wall. On this side, of course, the pressure is pushing in the positive X direction. So I'm going to have a positive force resulting from this calculation. So those are my force equations. I need to just take these integrals. They're very easy integrals to take, so really not a problem. The right-hand force is going to be, I pull that W just out, so minus W way out in front. And I've got P naught Z minus rho air G Z squared over 2, all evaluated at negative 5 and 0. So no problem with that, simple. And the second integral, the left-hand side integral is basically the same integral, which is W, and I got P naught Z again, and minus, of course, this time rho water, G Z squared over 2, evaluate at minus 5 and 0. So very simple integrals, so that's easy, and I can take those integrals, anyone can take those integrals. So those are my integrals, and I'm going to plug in my limits of integration. So on the right, I'm going to do this a little bit more carefully. I got some weird minus signs floating around. I got minus W, and when I plug in 0, I get 0 minus 0, right? So that's easy. And then when I have the second term, when I plug in negative 5, I get, now I'm doing the minus though, because it's the second term. So it's negative 5, so minus 5 P0. And then I'm putting in negative 5 here, which gives me a positive. So that's going to give me a negative again, because it's already negative, rho air G, and then 25 over 2, because negative 5 squared is just 25. So those are both going to end up positive because they have a negative sign out in front of them. And the second, on the left-hand integral, it's going to be the same thing, except I have a W in front instead of a negative W. So I have, once again, 0 and 0. So 0 minus 0 when I plug in 0. And then minus, then I have negative 5. So I have negative 5 P naught. And then negative rho water, G 25 over 2. So those are my two terms. I'm going to clean those up. On the right-hand side, I've got negative, positive, and positive. So it's going to be, these are all positive, and they're going to have a negative sign up front. So it's negative W, 5P0 plus rho air G 25 over 2. And on the left-hand side, I have no negative sign out in front, but they're both negative with negative signs, so they're both going to be positive. So once again, 5P0, and then plus rho water G 25 over 2. So I have positive force from the left, that makes sense, pushing the wall to the positive x direction, negative force from the right, pushing it back the other way. My net force, of course, is just a simple addition of these two terms. So I take my net force, and that's just F right plus F left. So my net force is equal to W 5P0 plus rho water G 25 over 2 minus W P naught 5 plus rho air G 25 over 2. I'm going to clean that up. I can see that this term and this term are going to cancel, and these two terms have identical forms except they have rho air and rho water. So it's going to be W times 25 over 2 times G times rho water minus rho air. And that's the answer. Obviously, I'm going to plug some stuff in here. So it's 4 meters for the width, 25 over 2 meters squared, because that was actually a meter thing, 9.81 meters per second squared. And this, I could put in, if I want, just water's density, as we've discussed many times. Air density is not significant compared to water. Air is 1, water is 1,000. So whether you want to put in 1,000 or 999 here, it doesn't matter. So there's my answer, I hope. So I'm going to go ahead and calculate it out here with my great calculator. So I have 4 times 25 divided by 2 equals times 9.81 equals times 1,000. And I get 490,500. So my net force is equal to 490,500 newtons. All right, so that's great. That is the answer. There is another way to do this problem, which I think Tom was the one who pointed it out. Because the pressure distribution is actually linear on the wall, it probably works to just take the midpoint pressure and apply that over the entire wall. So we could see if that works. That's actually a pretty easy calculation. So this would be the midpoint pressure would be at minus 2.5 meters. So if I apply that pressure would be P naught plus rho water G at 2.5, two minus signs, of course, working on each other. So I get 101,000 plus 1,000 kilograms per meter cubed times 9.81 times 2.5 meters. So what does that give me? 101,000 plus 1,123 times 9.81 times 2.5 is 125,525. So that's on one side of the wall, but in fact, I'm going to also subtract the other side pressure. I'm going to treat it as just P naught. So I'm going to subtract, I'm going to use gauge pressure here. So I'm going to subtract P naught. So that's going to give me just the minus 101 fridge. That didn't work. Hold on. That's the gauge pressure is 24,525. If I take that and multiply it by the area, which is just 4 times 5, so I have 24,525 newtons per meter squared of gauge pressure times 4 meters times 5 meters. What does that equal? 20 times 24,525. That's the same answer. So because the pressure distribution along the wall is linear in Z, we can take the pressure at the halfway point and just use that pressure as the pressure on the whole surface, that whole surface of the wall. And that gave us exactly the same answer. So, sorry, 490,500 gave us exactly the same answer. So that obviously is much, much more efficient. On the other hand, I really do want you to understand that in order to get real forces on walls, you need to take this integral across the entire surface area of the wall, because that pressure may not be changing only in the Z direction, and it also may not be changing linearly depending on the type of problem that we have.